In section 11.1, we are going to look at how to do derivatives of logarithms. A reminder about notation. When you see ln a, the ln stands for natural logarithm. A natural logarithm always has a base of e, and the argument is what you are taking the logarithm of, and in this case, it is the a. When you see the word log and a subscript, then you are doing a logarithm of base b, where the argument is a. First, we're going to look at the derivative of natural logs. When you see this d dx notation, that means that you are doing the derivative where the variable is x of whatever's in the brackets. So if we are doing the derivative of the natural log of u, then that derivative is 1 over u. Remember, u was the argument. And then du dx means do the derivative of the argument. So what you want to think to yourself to do the derivative of a natural log is 1 over the argument times derivative of the argument. To do the derivative, anytime you have the word log, L-O-G, it doesn't matter what the base is. This is the formula that you are going to use. You are going to do 1 over the natural log of a. Notice that a was the base of the logarithm. Take that times 1 over u, which is the argument, times du dx, which means the derivative of the argument. On our first example, we want to find the derivative, and our example A is y equals the natural log of x minus the natural log of the quantity x minus 1. Because each of these terms is a natural log, we can go straight into doing the derivative. And the derivative for a natural log, you do 1 over the argument. The argument of the natural log is what you are doing the natural log of. So it would be 1 over x times the derivative of the argument. The derivative of x is 1. Now move to the second term. 1 over the argument, x minus 1, times derivative of the argument is 1. If we clean that up, we just get 1 over x minus 1 over x minus 1. What you are going to find, however, is that they want you to write the answer as a single fraction. So in a problem like this, where you have the fractions with two completely different denominators, then the LCD is the denominators multiplied times each other. So what that means then is that the fraction on the left is missing the x minus 1 part of that denominator. But if I'm going to take the bottom times x minus 1, I must also take the top times x minus 1. Moving over to the second fraction, it is missing the x portion of the denominator. So we need to take the top and the bottom times x. Now we're going to actually do the multiplication. 1 times x minus 1 is x minus 1. You don't need to distribute on the bottom. You can just leave it as x times x minus 1. Minus 1 times x gives me x over x times x minus 1. Now that I have a common denominator, I can write this as one fraction. So I would have x minus 1 minus x over the common denominator of x times x minus 1. But notice that we have x minus x, so the numerator simplifies to be just negative 1 over x times x minus 1. On example B, we have the function f of x equals x squared times the natural log of the quantity 2x plus 3. What you need to note on this one is that there is a multiplication in here between the x squared and the natural log. So this is a product rule where x squared is the first and the natural log is the second. So to do this derivative, we're going to do the first as given times derivative of the second. Since it's a natural log, we have to do 1 over the argument of 2x plus 3 times the derivative of the argument, which is 2, plus the second left as written times the derivative of the first, which is 2x. So cleaning up a little bit, the first term would be 2x squared over 2x plus 3. And then the other thing we're going to do, just to make it more readable, is bring the 2x out to the front of the logarithm so that you can tell it's not part of the argument. There is nothing else that you need to do to that. That would be your answer. Before we begin our next example, I want to look at a review of logarithm rules. It's probably been a while since you've done this, and you may well have forgotten what these rules are. If you are taking any logarithm, doesn't matter what the base is, any logarithm of x times y, you can split that into the log base a of x plus the log base a of y. Split it into two of the same logarithm that you started with, but it's addition between them, and the first argument is x, the second argument is y. Just like that, then, if you have division in your original argument, you can split that into subtraction of two separate logarithms. If you are doing a logarithm and you have a power on your argument, you may drop the power to the front and make it become a coefficient of the logarithm, and then the argument stays the original argument, whatever it was. The reason that we want those logarithm rules is to do the derivative of a problem like g of x. We could do our derivative of a natural log rule to this problem as it's given, but it's much more difficult to do. If we just use our logarithm rules first, it gives us a much easier derivative. So we are first just going to rewrite g of x. This is division in my argument, so I'm going to split it into subtraction, where the numerator is the first argument and the denominator is the second argument. Notice that because I had natural log in my original problem, what I use as my logarithm in the spread out version is also a natural log. Now that I have two separate logarithms, I can do my logarithm rules for derivatives. So the derivative of this will be 1 over the argument times the derivative of the argument minus 1 over the argument times derivative of the argument. So just to see what we've got at this point, we have 3 over 3x plus 5 minus 1 over x minus 7. We don't get to leave it as two separate fractions. WebAssign requires you to make it one fraction. So the LCD is the two denominators multiplied together. So on the left-hand fraction, I need to take it times x minus 7 over x minus 7. And then on the right-hand fraction, I need to take it times 3x plus 5 over 3x plus 5. So if I do that, the numerator of the left-hand fraction, distribute your 3, you're going to get 3x minus 21 over our LCD of x minus 7 times 3x plus 5 minus 1 times 3x plus 5 gives me 3x plus 5 over our LCD, x minus 7 times 3x plus 5. Now that I have a common denominator, I can subtract my numerators and leave the denominator the same. It will become 3x minus 21 minus 3x minus 5. Be careful that you distribute that negative over x minus 7 times 3x plus 5. Notice that 3x minus 3x is 0. So our final answer then is negative 26 over x minus 7 times 3x plus 5. On example D, we want to do the derivative where our function is the natural log of the square root of two quantities that are being multiplied. We are going to put our logarithm rules into some serious use here before we even begin trying to do the derivative. It will take a little bit of time to get there, but it makes doing the derivative so much easier. If I left this logarithm as it is, I would have to do a chain rule with a product rule inside it. And that's so much more difficult than what we will have when we get to a simplified version. The first thing to remember is that a square root is the same thing as a 1/2 power. So I'm going to rewrite this as the two quantities multiplied being raised to the 1/2. Now, remember, as a little aside here, if I had xy that I was raising to the third, I could make that x to the third, y to the third. We are going to use that same concept on our two quantities. So we are still rewriting y. We're going to have the natural log of x plus 1 to the 1/2 times x minus 6 to the 1/2. It's kind of the same idea as distributing. Each of those items gets that power. Well, now think about that this is multiplication in between those two quantities. So we can use the logarithm rule that says rewrite it as the two items separated. It's two separate logarithms with addition between them. Now we're going to use one last log rule where when you have a power, you drop it to the front. So we're going to take these powers and drop them to the front, and this is just a log rule. So this will become 1/2 times the natural log of x plus 1 plus 1/2 times the natural log of x minus 6. Once you are to the point where you have natural log of an argument, there's no power on the argument, there's a single item in the argument, then you are ready to do the derivative. Think back to when we were doing derivatives. If we had something like 4 times x squared, we kept the 4 and made it 4 times 2x, which is 8x. So when we had a coefficient, we just kept that coefficient. We're going to do that same idea here. we have coefficients on each of these logarithms of 1/2. So we're just going to keep those coefficients. This will become 1/2 times. Now let's do the derivative of the natural log. 1 over the argument times derivative of the argument. Move over to the second term. Keep your coefficient. Do the derivative of the natural log. 1 over the argument times derivative of the argument. Well, cleaning up our fractions, we have 1 over 2 times x plus 1 plus 1 over 2 times x minus 6. Because each of these denominators already has the 2 in it, that's going to be part of the LCD. But we also need each quantity. So my LCD is going to be 2 times x plus 1 times x minus 6. So on our first fraction, we are missing the x minus 6. So we're going to have to take top and bottom of that first fraction times what we're missing, the x minus 6. For the second fraction, what's missing is the x plus 1. So we're going to take that times x plus 1, top and bottom. 1 times x minus 6 gives me x minus 6 over 2 times x minus 6 times x plus 1 plus 1 times x plus 1 gives me x plus 1 over 2 times x minus 6 times x plus 1. Now we can just add our numerators and leave the denominator the same. And then notice that we've got some like terms here. X plus x gives me 2x. Negative 6 plus 1 gives me negative 5 over 2 times x minus 6 times x plus 1. I did some editing on the notes, and when I did some editing on the notes, I forgot to edit the letters. So we are skipping from example D to example G. And on example G, we have y equals, and then we have this brackets raised to the 4th, and inside the brackets, we have a natural logarithm. The reason I stressed that is because the natural log is inside what's being raised to the 4th. So I wanted you to see that this is not a case where you can drop the power to the front of the natural log. The power is not on the argument. The power is on the entire natural logarithm. So because of that, we are going to have to use the chain rule. We haven't done that for a while, so it's going to be a little bit of review here. The chain rule says, take the power that's outside the entire function and drop it to the front. Leave the inside the same. So nothing inside is going to change. Now your new power goes down by 1. Then we do the derivative of the inside. The derivative of this inside, because it's a natural log, will be 1 over the entire argument, 5x squared minus 3x plus 2, times the derivative of that argument, which will be 10x minus 3. So what happens on this one is you have to recognize that we can think of this whole part to the left as being over a 1 and the 10x minus 3 as being over a 1. And so multiplying all those fractions, we are just going to have the 4. We're going to have the quantity, which is our natural logarithm, raised to the third, times the quantity of 10x minus 3. All of that goes over 5x squared minus 3x plus 2. Do not try to simplify this in any way. You cannot. I know that the denominator matches what you're doing the natural logarithm of, but you cannot simplify that because part of it's an argument and part of it's not. So this is your answer. On example H, our function is a log base 4. As soon as I see the word log, I know I need to use the other logarithm formula. Do not worry about memorizing this formula. I will give it to you. This is the derivative formula for any logarithm that has the word log in it. For this problem then, our derivative will be 1 over the natural log of the base. Our base is 4. We take that times 1 over the argument. Our argument is x cubed plus 5x squared plus x. Take that times derivative of the argument, which will be 3x squared plus 10x plus 1. Again, recognize that we could think of this as being over 1. So now multiplying those 3 fractions, 1 times the quantity, gives us the quantity, 3x squared plus 10x plus 1, over the natural log of 4 times x cubed plus 5x squared plus x. You cannot do anything else to this. That is your answer. On example 2, we are going to find the equation of a tangent line to the function that we are given at the point 1, 0. And the function that we are given is y equals the natural log of x over x to the 4th. And we need to do the derivative of that function because we need a tangent line. So, derivative of this function is going to require the quotient rule. We have a variable in both the numerator and the denominator. We can't simplify that. We have to use the quotient rule. So we're doing a lot of review on rules here. Quotient rule says start with the denominator, the low, times derivative of the high. The derivative of the natural log of x is 1 over x times 1, which is the derivative of x, minus high times derivative of the low is 4x cubed. All that goes over the denominator squared. So x to the 4th times 1 over x times 1 gives us x to the 4th over x minus, I'm going to put the 4x cubed out front so that we can tell it's not part of the argument of the logarithm, and that's all over x to the 8th. X to the 4th over x simplifies to be x cubed minus 4x cubed, natural log of x, all over x to the 8th. I can factor out x cubed in the numerator. if I factor out x cubed, I would be left with 1 minus 4 times the natural log of x, and all that goes over x to the 8. Now I can simplify the x cubed over x to the 8. So what's going to happen is the x cubed will go away. We'll take out 3 of the 8 and leave 5 of them. So the final form of my derivative will be 1 minus 4 times the natural log of x over x to the 5th. Remember why we needed this. This is the formula for slope of the tangent. So we're going to use that to find the slope of the tangent. And the variable in there is x. And if you look at our original point, our x value was 1. So we're going to put 1 into that derivative. Anytime you have a logarithm of 1, that equals 0. So we are left with 1 minus 0 over 1, which is just 1. So we now know that the slope of the tangent is 1. Our problem asked for equation of the tangent. So I'm going to go back to that point slope form where the y stays as the variable. The y of my point was 0. My slope is 1. X is the variable. The x of my point was 1. So I have y equals x minus 1. Here is the equation of my tangent line. On example 3, we are told that the cost in dollars of producing X units in thousands of a certain product is the function c of x equals 20 plus the natural log of the quantity x plus 1. Part A says to find the formula for marginal cost. Remember, marginal anything means derivative. So we need the derivative of the cost function. So c prime of x, the derivative of 20 is 0 plus, this is a natural log, so we're going to do 1 over the argument times derivative of the argument. And then that just cleans up to be 1 over x plus 1. Question B says, find and explain the marginal cost for 3,000 items. What you need to be careful of here is that it says 3,000, which is 3 thousands, which therefore means x is 3. That's what we're going to put into our marginal cost formula is 3, not 3,000. It's how many thousands is it. So c prime of 3 will be 1 over 3 plus 1, which is 1/4, which is 0.25. So what does that mean? If it's $0.25, that means that it's 25 cents. So the cost is, it was a positive 25 cents. So it is increasing 25 cents when changing from 3 thousands, and it's always to the next one, to 4 thousands. And that is your interpretation.